Hello and welcome back to this ASAP tutorial. This first example will be about building a basic radiometer in ASAP. Now, this isn't so much a realistic radiometer as much as it is a conceptual radiometer that shows you the basic models in ASAP and allows you to understand some of the basic functionality. Here you'll be able to learn how to design an optical object. You'll learn how to define your variables in your system. You'll learn how to set up the basic commands as well as trace rays and do a ray trace analysis on a surface. Without further ado, let's show what the final result will look like. This is the example we will be looking at in ASAP. As you can see here, this is our quote-unquote radiometer that we will be examining to show ASAP's features. It will be light that goes through a singlet lens through this tube and hit this detector on the side, which is just a circular surface. You will see that this is how the light rays will traverse through it and hit the detector on the end here, and you will see how light goes through and bounces back. You will also be able to model these light rays passing through the system and hitting it, and you will also learn how to create these irradiance plots inside the system, such as this, as well as this chart here that shows you both the 3D view and the 2D view. The other thing that's worth noticing is when we produce these graphs, we can move the crosshairs, and these lines here show the diagram of the intensity versus X and the intensity versus Y of this crosshaired section. Without further ado, let's start the tutorial and start from the very beginning. Without further ado, let's start ASAP from the very beginning. When you first open the system, this is what you'll see. You'll see the main toolbar up here, you'll see the workspace over here to the left, and you'll see the input-output information over here, including processor nodes such as local and remote. You can also put commands down here, and you'll be able to see what your working directory is down here. And you can see that it's users, documents, bro, ASAP next generation. With that, we will first start by setting our preferences for how we want the system to look. So we go over here to preferences and we'll go over them. First, we have the general open last used files on startup. This will open the last files we have. Update working directory files in the files tab. So that will do that here. HTML help allows you to use our help guide, and you allow customization of the working directory and display, as well as show the splash. Now, with the optics manager, we want to set our facet resolution for TU and V. Facet resolution is how ASAP itself it's the resolution of the geometry represented in the system, and we'll explore that later as we continue on through the tutorial. We will discuss on warn on interpolation range. This means the range of light waves in one field versus another, and it makes sure that the range of the light waves in the system is the same basically throughout the system. Enable variable list from text to edit windows. This will allow you to pull up variables in it and automatically update the viewer. This means as soon as you create a new geometry, you'll be able to update the viewer. Now with plot viewer, we want to set it to 0 and 100 and have these values checked here. And for 3D viewer, we want to have basically these. Be sure to set at the global origin rather than the rotation center, and display axes and auto size axes on startup. We also want for the input window these values checked, not suppress beeps. The beeps allow you to basically see when things are running and such, and we have these put in forth as well. And with that, we have all the preferences we want set up. So we press OK, and you might see a startup request on some of them, simply restart ASAP if that is the case. And with that, let's get to designing our geometry. Now, firstly, we're going to go to the Geometry tab, and we're going to create a couple of branches within the system for the different parts of the radiometer. So first we'll create a central geometry branch. So you can press Ctrl-Shift-P or just simply right-click this. And we're going to call it radiometer. We're also going to have it all capitalized. This is simply because it aligns well with the code, especially if you want to convert it to an INR file, which I will show you later, probably towards the end. So and then we put another geometry branch. So one is for the singlet, geometry branch. One will be for the baffle, and one will be for the detector. Insert geometry branch. So next we're going to jump to the variables, and there are a couple of variables we will want to define. Sometimes you can define the variables later, and you might not be doing that as you build it, and sometimes you'll notice some variables dependent on another. This is always a good place to use it. So let's define the variables here. So we double click here and let's fill them in. So we will have lens locations, lens lock, and that will be at 0. We will have lens diameter, and that will be 50.8. And you can, and for the record, I'm pressing the tab key to jump between these. So we have detector diameter, and that will be at 50. Detector distance, and we'll press the tab again, and that will be 63. And we will have the baffle diameter, and that will be 62.5. And I'm going to put in my own another one, which will be lens curvature, or this will also be the radius of the lens. This will be the curvature of the surface, and I'm going to put that at 53. And let's press apply. Now we have the variables that will be used throughout our system. And from here we can start going over this different parts. We'll first start by defining the singlet. So we would go down here to singlet, right click, and insert geometry. And for this we're going to create an optical geometry. So we'll call this one front, because this will be the front of the lens. We have the location at lens location, and we will have the radius of curvature being the lens curvature and the lens curvature. You'll also notice that your variables are listed in alphabetical order as compared to the input order that you put them in. And the aperture will be an ellipse with a semi-major axis of our lens diameter divided by 2, and lens diameter divided by 2. And so with that, I believe that's everything, but we can always come back. So let's press apply. And thus we have our first lens. And this is actually kind of interesting. This is not supposed to be flat on the top. Let's see what we did wrong. So modify. So we have front Z lens diameter. Oh, this was the mistake that I made. I inserted a conic constant here. That should remain 0. And this is the wonderful thing about ASAP. You can always correct your mistakes later. So we press OK, and now we have a nice curved surface. That's exactly what I was looking for. Next we will create the back of the lens. So we press insert geometry again, and we'll press optical, and this time we'll be sure to put it to 0. This time, however, the lens curvature will be negative. This will have it go from one way to the other way, and we will have the lens location at lens location plus 16. And with that, let us press apply, and thus we have these two wonderful little curved surfaces. But it's two curved surfaces, not a lens. So we're going to insert a new geometry. Actually, before that, I do want to change the name of this, so I'm going to right click, press modify, and change it to back, and press apply. And we're going to insert geometry. This time, however, instead of optical, we're going to select tube. And the location will go from lens location as the first one of our first lens to lens location plus 16, which is the position of our second lens. Semi-major axis of the lens diameter, and enjoy the flight above our head. I don't know if you guys heard that. So lens diameter divided by 2, lens diameter divided by 2, lens diameter divided by 2, lens diameter divided by 2. And we're going to have a starting curve of 0 and an ending curve of 0. Again, the values between 0 and 1 say how much of an ellipse it's like versus how rectangular the shape is. And as you know, we want it to be an ellipse, or rather a circle. So now we press apply. And we see that I made a mistake here. Let's see what it was. So bounded by two curves. Yep. So axis type 2, lens location plus 16, lens diameter. Oh, this is not supposed to be 1.5. Yeah, you need to have multiplication in the system when this happens. So let's press apply again. And thus now this is the shape we're looking for. However, you'll notice here that you have these, what's the word I'm looking for? You have this cone around it, cylinder around it, and we actually want it to end at the lenses and be bound by these two curves. So luckily we have a way to bind it, and that is the bound command. So we press the bound, and we want it to have and for the back and front. The edge will not be selected because, well, it is the side we're working on, and so the front will be plus, and it will go to the back, which is negative. And then we press apply, and thus we have our lens. Now the problem with this system right now is it's a geometrical construction. Right now it doesn't have any of the optical properties that we want in the system. So as a way to do that, we are going to go here to our singlet branch, and we're going to, and this is what one of the values of branches is, you can put in one property for multiple geometries in the system. Specifically, we want to put it in the media. So the first media will be air, but the next one will be fused silica. So the way we go to fused silica is we press the select button here, and we search for fused silica. So we select it, medium 1 air, medium 2 fused silica, press apply, and thus you see the media applied here. Next we want to put in the coating, and the coating that we put in here is, give me a second to find it in my notes here. The coating that we're going to have is, it's going to be bare, and yeah, this part I'm going to put out. It's going to be, alright, let's start here. Next we're going to put in the coating here, and the coating we're going to have is, we're going to have it bare, and in terms of options we're going to have it transmit only. So this will make sure that all the light that passes through will be transmitted out after it's transformed via propagation through the lens. So we press apply and we have the coating. Now the thing is, we usually want to put in another type of coating on the edge. Now the thing is, with this system, we want the edge to be perfectly absorbing. This is because we do not want any light transmitting through the edge. So to do that, we click on the edge and we select coating. And the type of coating we're going to select for this is perfectly absorbing. So this way, everything in this, every light that goes through this is perfectly absorbing. So we press apply, and thus we have this system. One of the values of this is, say you want all of the geometry to have one feature except one side. This way, this property is applied to the entire singlet, but you can change the coating specifically for the edge itself. And then with that, we have completed making our singlet lens. One of the things we can do is we can actually select the singlet, right click it, and we can actually make it transparent, so we can see through it through here. And by pressing the scroll wheel on here, we can actually navigate ourselves and rotate around the system, as you can see here. And if you scroll the scroll wheel back and forth, you can then zoom in and zoom out. Now the next part we're going to work on is the baffle. This will be the surface in which our system is enclosed. So to do that, we right click and we press insert geometry, and we're going to select the arc. Now we're going to name our arc baffle, arc baff. We're going to set it along the z-axis rather than the x-axis, and we're going to have the location to be the lens location, because we want it to start at the beginning of the lens. And for the arc radius, we're going to have baffle diameter, and select apply. This is another mistake that I made, so let's right click. I actually want it to be baffle diameter divided by 2. This is the wonders of working with optics. You have to remember the difference between radius and diameter. So we press apply, and thus we have this shape right here. We can also now insert another, we can also create the object as being swept. The swept command will put a surface starting here going to a certain distance we want. So we want to do the curve arc baffle, which we just created, and sweep in the following direction. So you have A, B, C, and the sweep distance, however, will be the detector, detector distance. That will be from here all the way to the detector, and our values will be A is 0, B is 0, C is 1, and these are, local coordinates of this surface with respect to this surface. So we press apply, and thus we have the system as you can see here. Now you can only see the lens from this angle, so let's select the swept, let's select our baffle, and let's actually make it transparent, and thus you can see the lens inside and the baffle diameter. The last thing we want to add is the detector, and this is going to be insert geometry, and we want it to be a plane. And rather than the aperture being a rectangle, we want it to be an ellipse. Semi-major excess of detector diameter. And detector diameter again, divide by 2. Ellipse, orthogonal to axis, and let's just call it detector plane. And let's press apply. And you'll notice once again we can modify it because I made a mistake. So I wanted it to not be at z location equals 1, but at the detector distance. Press apply, and thus it jumped over here. Now we have the entire geometry built. Now it's time for the part you're all waiting for. I know you could probably design something like this in CAD, but now it's time for the optical analysis that you've been waiting for. So for here, what we do is we want to go to sources. We can select whatever source we want. I'm going to go with a polar source for this system, with a radius being, we'll set the radius to be the, let's have it be 25, which is, you'll remember our lens is about, I think, 63, so the radius of our propagating light will be a little bit smaller than the lens that we have here, and we'll have 21 rings. Total flux being 1, our wavelength will be 550 nanometers, and our ray type will be collimated. In other words, this will be a collimated light source, and for location, let's start it at -2. And this will, rather than starting right here, it will start about 2 millimeters to the left. So let's press apply. And with that, let's do a source analysis. And for our source analysis, we're just going to select all. This will allow us to have a really quick sanity check to make sure everything worked. So let's press run optics. And so you'll notice nothing happened here, but we got some input-output information down here in our box. So you'll see that, yep, 1387 ray fluxes were altered. They were created, so 1387 were produced, 1387 were altered. That means they were changed going through a system. And you'll see that all of the rays propagated from object 0. Object 0 in our system is always our source. So, looks like a lot of these values seem to make sense. So, now we're going to set up our trace. Now for our trace, we're going to select plot rays and plot geometry. If I didn't have this selected, then it wouldn't show this figure of everything, it would just show the rays. We do want to see the rays, and we're going to have it plot the facets, and we're going to have it display in 3D viewer, auto scale. This is for our 2D window, and we want it to be Y and Z. For the record, X and Y would be this direction, and this is Y and Z. And if we were to see from the top, this would be X, this would be X and Z. So this is the system we're going to look at, and we're going to insert it into our system here. Now, from here, we're going to run our system again to make sure that it runs. And you'll see that we had the 2D viewer come up here in the YZ direction, and you can see how the system plotted. And you can see this also plotted as well. And you'll see these white lines being the 1300 rays that are propagating through our system. So that worked all fine and dandy. Now we want to actually introduce the trace analysis. So give me a second to tune up on my notes. So for our trace analysis, what we want to do is we want to select consider objects, and this will allow us to choose which objects we want to consider. Now we set up a detector all for this. So firstly, we would unselect all, because if you don't, you'll notice you aren't able to click off these. So we will select all of those that we don't want, except the detector plane. And then we press apply. And then now that we have our object considered, we can choose the type of analysis that we want. And we want to do an irradiance analysis. So it will auto scale. We don't want it to be, actually we do. We want it to be X and Y. Sometimes you will have X, Z, Y, Z, but this is the correct one that we want. And we also want it to, and the other one that we want to have is the type of result that we want is we want the results to be a picture, and we also want to have an isometric curve. So plot every 1th line of distribution data. Yeah, let's do that. And with that, let's run our system and see what we produce. So we reproduce again the system, the 2D viewer, and from here you also saw that within the plot we also got an XY view. If you want to see the other view, you would press the back button and you're able to see the rays from this surface as well as the surface of the detector. And that's where you see these concentric lines from. Once again, and also before I made it transparent, let's actually hide it entirely. So let's press the hide button and you'll see how the light goes through the lens and how it hits the detector. And we can see here that it created a second one. Let's ignore that. And we can see our system here. So you'll be able to see these light blue lines out here, but you can certainly see the peak that a bunch of them are centered here. And you're able to also see a 3D plot of it right here. And so with that, you can rotate, you can move around, and you can zoom in. So you zoom in like this, and you can see the peak is at the center, and everything else is here. You can modify for the resolution of how many distribution data you want in this, and these are the curves that you see available. Now, the great thing about our system is you'll notice that we set it up so that we can change the variables. Say that you just wanted to change this detector distance. Actually, before we do that, so let's go back to the optics viewer. Say you wanted to check a distance a little bit further away. You can set the detector distance as being 73 and press apply. You'll notice that it got a little bit longer, and the thing that was nice is you'll remember that both this tube as well as the detector position were both based on detector distance, and both these values changed at the same time. So let's run optics again, and now it's a little bit further. You see slightly more circles, and I believe both of them are, so this is our initial display and this is our second, and you'll see that because we're a little bit further away, the light diverged a little more. So you'll see that the ones that were a lot more towards the center before, the image got a little bit more peaked. And this shows you the basic introduction. This is meant to be more of a one-on-one tutorial and help you see the systems as they are available. Anyway, we hope that you found this first lecture valuable and hope you all the best on your great optical analysis plans in the future, and we hope you will continue to work with us. Have a wonderful day. Hey, Amr here. A really quick note that I forgot to add in my initial recording is you'll see this workspace right here. One of the really important nuances on this is where you save your system, because it's not by going to File, Save. You'll notice here that there's no save options here. They're not available. If you want to save your optical geometry build, you have to go here and press the save button in the workspace. My apologies for not hitting this earlier, and hopefully this quick interlude will help you guys later. So yeah, I'm just going to create a radiometer. Anyway, hope this helps, and thank you as always for your time.